So now we're going to have a look at another question from the 2020 HSC Advanced Maths paper. So this is question 26. It's a finance question, financial mathematics question. Tina inherits $60,000 and invests it in an account earning interest at a rate of 0.5% per month. Each month, after the interest has been paid, she withdraws $800. The amount in the account immediately after the nth withdrawal can be determined using the following recurrence relation. Use the recurrence relation to find the amount in the account immediately after the third withdrawal. Okay, so they've told us use the recurrence relation. So A of 0 we know is 60,000. This is the amount in the account initially. So we just need to find A1, A2 and A3. So A1 is 60,000 times 1.005 minus 800. So if we plug this in to our calculator, we'll find this is 59500. And this makes sense. What we're doing here makes sense because the 60,000 is being increased by 0.5%, which is the interest, before the 800 is taken out. And that's what we have. A2 is going to be A1 times 1.005. This amount that was left over will be increased by 0.5%, and then 800 will be subtracted. When we round this, we find that this is, or when we calculate this, sorry, we'll find that this is 58997.50. So this is what we get from the calculator. We're just calculating these. And then A3 is A2, which is this amount, times 1.005 minus 800. And this gives us 58492, when rounded to two decimal places, 0.49. And two decimal place rounding is standard here because this is dollars and cents. So the amount of money in the account immediately after the third withdrawal is $58,492.49. If you are using a different financial method that is not the recurrence relation, it's actually possible for you to get a slightly different answer depending on how the method rounds and depending on how the method calculates. So in finance, in the actual field of finance, there are lots of different methods. They sometimes end up off from one another by a little bit. So if you are using an alternative method, you might end up off by 5 or 10 cents or $1 or something like that. That's not uncommon. But they've told us to use recurrence relation, so using that method here is what we want. 1 mark is given for working, pretty much, and 1 for the answer. So there's 1 mark for working and then 1 mark for the final answer. So this is all part A. This is all part A. In part B, this question continues. It has 2 more parts. Calculate the amount of interest earned in the first 3 months. Well, at the end of the 3rd month, the balance at the end of the 3rd month is $58,492.49. And $2,400 has been withdrawn from the account in terms of the 3 $800 withdrawals. So if we add 2400 to this, this gives us 58492.49 plus 2400. This is $60,892.49. The difference between this and 60,000 is $892.49. Now, this must be the interest, right? The extra money has only come from interest. So that means when we add the withdrawals back on to the amount in the account at the end of the 3rd month, the difference between 60,000 and whatever amount that is must be the interest. And that is the answer here. That is the correct solution. This is one way you could do this. There's a few different ways to do this. In the 2 marking criteria, you'll get 1 mark for your working and 1 mark for your solution. The working will vary quite a lot. In financial calculations, there are a few different ways to do things. This is one of them, and this will get you both of the marks. So now we have part C. Calculate the amount of money in the account immediately after the 94th withdrawal. So the amount after the first withdrawal was 60,000 times 1.005 minus 800. The amount after the second withdrawal was the amount after the first withdrawal times 1.005 minus 800. And so on. This pattern continues. Each time you've got A3 is A2 times this, A2 is A1, A5 is A4, and so on. If we plug A1 in, this tells us that A2 is actually 60,000 times 1.005 minus 800 times 1.005 minus 800. And if we write this in a slightly different form, if we expand the brackets, this becomes 60,000 times 1.005 squared minus 800 times 1.005 minus 800. We can do this again. So we can do this for A3 as well. And if we do this for A3, so if we take A3 and we have A2 times 1.005, so A3 is A2 times 1.005 minus 800. If we let this go where the A2 is, this becomes 60,000 times 1.005 squared minus 800 times 1.005 minus 800, all times 1.005, all minus 800. If we expand this out, this becomes 60,000 times 1.005 cubed minus 800 times 1.005 squared minus 800 times 1.005 minus 800. You should be able to see a pattern forming here. After the second month, we had the initial amount times 1.005 to the power of 2. And then we had minus 800 times 1.005 to the 1 and 800. After the third, we had 60,000 times 1.005 to the 3. Then the 800, 1.005 squared, 1.005 and 800. So you can see a consistent pattern forming here. And we can write this as an nth sum. So this implies after the nth period, we're going to have 60,000 times 1.005 to the n minus 800 times 1.005 to the n minus 1 plus ... all the way down to 1. And we are inferring this from looking at what happens when we go from A1 to A2 to A3. We are getting this format from the recurrence relation. Now, this is something ideally you should have done in class. This should not be the first time seeing this. You should have done this many times, building these summation formulas from iterations of the recurrence relation. When we have this, we can use this in order to calculate what's going to happen after the 10th month, the 50th month, 100th month, so on. The only problem here is this. This is a long series of terms. It's a long series of terms, but they are all multiples of one another, because we have 1.005 to the n minus 1, 1.005 to the n minus 2, n minus 3, all the way down to 1.005 to the 0, which is the 1 term at the end. So we can write this, we can say the first term is 1.005 to the n minus 1. We can say the difference, so this is A, this is the first term. We can say the difference R is 1 over 1.005. And then when we think about this, the number of terms here, we go from n minus 1 down to 0. So this is going to be n many terms. So n is n. If we do it this way, this will tell us that this sum, it's a sum of terms in a geometric progression. This is going to be sum of terms in a geometric is first times ratio to the power of n minus 1 all over ratio minus 1. So this will give us the sum of n terms is the first term 1.005 to the power of n minus 1. So this is all just working, by the way. This is all just converting this long sum into a single term so we can calculate it. Times the ratio, which is 1 over 1.005 to the power of n minus 1 over the ratio minus 1. 1 over 1.005 minus 1. And then you can simplify this down. This was actually not a great way to go in this question. Leaving this as the first term and 1 as the last term, and using the multiplication factor as 1 over 1.005 actually made this all more complicated than it needed to be. We could have turned this whole thing around, and we could have said actually 1.005 to the n minus 1 plus ... all the way down to 1 is the same as 1 plus 1.005 to the 1 plus ... all the way up to 1.005 to the n minus 1. Here we would have had the first term is 1, the ratio is 1.005, and the number is n. And so our sum Sn in this case, which will pretty much already be simplified, will be 1 times 1.005 to the n minus 1 over 1.005 minus 1. And this is equal to 1.005 to the n minus 1 over 0.005. And so this was easier. This was better than this in this case, because it just simplified straight away. So if you can sometimes think about these things in terms of rearranging these series, it may make your life a little bit easier. It's not that this is wrong, this works, it's just more complicated. So now we know what the formula is going to look like. We know that the recurrence relation after the nth term, that the total amount in the account after the nth term, will be 60,000 times 1.005 to the n, and then we will have minus 800 times the sum we just calculated, minus 800 times 1.005 minus 1, sorry, 1.005 to the n minus 1 over 0.005. Now the question asks us, calculate the amount of money in the account immediately after the 94th withdrawal. So in this case, the way we've set this up, n is just going to be 94. So we have the amount after the 94th withdrawal, 60000 times 1.005 to the 94 minus 800 times 1.005 to the 94 minus 1 over 0.005. So now I'm just going to calculate this whole thing. 60,000 times 1.005 to the power of 94 minus 800 times 1.005 to the power of 94 minus 1, all divided by 0.005. This is going to give me A94 is 187.845 ... This is dollars and cents, so we need to round this to two decimal places. Therefore, the amount in the account after the 94th withdrawal is $187.85. This is two decimal places because it's dollars and cents. And this is the solution. So for this particular part, most of the question was just deriving a formula to find the nth term. Right? There was a lot of working. You didn't necessarily need this much working. This is used for teaching and demonstration purposes. But once you see these recurrence relations and you can build later terms in the recurrence relation into earlier ones, you can start to get patterns forming. You can then turn those patterns into general formulas. So that's what we did here. So to get a mark, you need an attempt to develop an A94th formula. So something like this first bit of working, starting to show that you can get patterns forming will be sufficient. To get the second mark, you need to find an expression for the 94th formula. So actually all of this and then this. And then to get the third mark, you need a correct solution. So you will have to have 187.85, and that is the exact answer in the marker notes. You will need that answer to get the third mark.